making ice at night, cooling at days, etc., etc. And that will allow us to cool that 6-story building as efficiently as possible. And in addition to that, to make the entire thing sustainable, and by sustainable I mean that you implement a measure today, somebody doesn't come tomorrow and change it. And if somebody's coming tomorrow to do something, then they'll be aware of what you were trying to do yesterday. And it's always that drive to improve and to sustain what you're doing. And so there's a need for a policy. And we developed an AC policy, and that policy spoke to a number of things which I'll outline very briefly soon. Issue number 2 involved power factor correction, which I'll speak to again later. We had several areas where we put in capacitor banks, as well as we changed out magnetic ballast to efficient electronic ballast. Issue number 3, we improved our lighting efficiency. That is, we went out and we changed out all the T12s, 40-watt tubes, to T8, 32-watt tubes. And we did that, and we were able to measure the results, and from there, I'll give you an idea of how we benefited further. We installed occupancy sensors as well. And finally, persons were saying, why are you moving from T12, 40-watt, to T8, 32-watt? What about LEDs? You know, that's the latest thing. Yeah, persons said. So what we did, as we have done for every other project, we did our own tests. We had small errors, we run our results, and based on that, we decided how we go ahead. So I'll share those results with you. In terms of refrigerant changeout, this is actual results from what we were able to accomplish. If you can't see this very clearly, I think there's actually a printed, my presentation is printed in your folder. You could probably look at the numbers more closely. But in a nutshell, what we did, we looked at some departments, administrative and special agencies, Department of Life Sciences, Social Sciences, Pre and Applied Sciences, and Humanities. And of those areas, we decided to retrofit a number of units. And what we were able to accomplish is that, one, based on the cooling capacity of that unit, we measured the current that was being drawn by the unit. That's in amperage before the retrofit exercise. And we logged that results for like a week. And then we measured it after the retrofit. And based on that, we were able to quantify how much less energy or less current that AC unit was utilizing. And so the relative percentages that you see here, it's given in kilowatts in this case, is from 23% as high as 27% to as low as 16.5% reduction. And based on that, JPS actually uses kilowatt hour as their unit of energy. That's how they bill us. So we're able to use that to calculate how much it actually would cost. Well, not how much it would cost, the actual savings. Now, this is in $2,006. And we were able to prove that within 8 months, this project would have paid back for itself based on the retrofit exercise. Now, we didn't go much further with this project after 2006, even though the numbers look this well. And one of the reasons was that we didn't have the AC policy developed as yet. And what was happening is that of these 646 units that we went out and we diligently changed out and we measured our results and we prepared a large booklet to show everything, we're getting ready now to go ahead and do the additional 1,000 odd. But you found that persons were actually going through, whenever the units need servicing, companies would come and change refrigerant back from the hydrocarbon and putting back the existing one. And so it wasn't sustainable in that sense. And we had to find a way to address that before we continued. We intend to continue now that we have the policy. The policy was completed last year, April, and so far we're having some success in that. And that's where I mentioned the policy here. The policy speaks to procurement, installation, usage, and servicing and retirement of units. So if, for example, if someone now wants to purchase an air conditioning unit, how it was before is that each department on the campus will get their own budget. How you spend that money is your business. They have that level of autonomy on campus. And it was put in place that way for efficiency. And not only that, but most heads of departments is somehow with a PhD or this and that. So you can't really tell these people what to do all the time. You know what I mean? They want to be able to do their thing. So they have that autonomy. They get their budget, they do what they want. So they just go ahead and buy a unit. And sometimes you find an AC unit cool and empty space with a big window open or an open space that is not enclosed. All these things existed on campus. So the policy sought to address that in that before you can purchase a unit, someone from the estate management department or myself will visit the area and have a checklist of criteria that had to be met to see if it satisfies or warrants a unit to be put in place. In addition to that, the policy would also look at future projects, to see if, we'll hold on for another month or two because so-and-so is going to happen soon and stuff like that. So we're able to benefit from that tremendously. And so far, the policy has guided us. For example, some heavy usage areas now have inverter AC units. They cost twice as much when compared to a conventional AC unit. But some areas on campus actually open 24 hours, like parts of the library, etc. So in cases like those units pay back for themselves very, very quickly. So you can make a case to say, we need money for this, and this will be the case. And once you have in numbers and you make a proper presentation on campus, you normally get support. So the final one about the service park, I mentioned that before. Now, here are some numbers I'm about to share with you for the power factor correction project. Now, the power factor in general, it has to do with the impact that your electrical load. So let's say you plug in a motor into your circuit. How does that impact the overall efficiency of how energy is being utilized? For example, you have two variables, kilowatt and kVA. I want to look at kilowatt as the real power. So how much power do I really need for that motor to spin? Or what is the rate at which the motor is using power? And when I speak about power, it's a little bit different from energy. Energy is like a total energy. As Einstein would say, E equal mc squared, but the total ability that a body possesses to do some work. While power now is the rate at which you're using that energy to do the work. So in this case, we talk about kilowatt and kVA. Kilowatt being real power and kVA being apparent power. And so kilowatt, real power, how much of its energy is actually being used, while kVA is the total amount of energy that you had. And so there is sometimes, well, oftentimes, in fact, all the time, kVA is greater than kilowatt. But the disparity or the ratio of kilowatt over kVA gives you a measure of the efficiency in terms of how efficiently that load is using the energy. And we'll call that power factor. And so when we talk about power factor correction, we're actually trying to improve the efficiency of that load, how efficiently would it utilize the energy. And so what we did here, in the background here, you see, in the background, that scatter that you see there is actually a scatter plot. Use Microsoft Excel to plot some 92,000 data points. On campus, we have a system we call it our energy management system. If I had internet access here, I'd be able to log into it, and I could show you exactly how energy is being used in real time in several departments on campus. And we have that system up since 2006. And we have been logging the data. For every 15 minutes, we store all the energy parameters from kilowatt, kVA, amperage, voltage, kilowatt hour, everything. And we store that data in a database, so we can pull from that whenever we want and show the trends or the energy trends. And so whenever we implement a measure, we can see the impact it has